And just like that, we made it to the end of the chapter. So let's see what we have left on this chapter. So we're going to be talking about fission and fusion. In addition to that, we're going to take a quick view to see how a nuclear plant works. And to be able to talk about that, we're going to have to talk about something called the mass defect and all the energy that is associated with that. So let's start with this. So I just finished talking about energy. So nuclear reactions, like a nuclear bomb, for example, they generate a lot of energy. There's no question about that. The amount of energy that can come out from a nuclear reaction is excessive amount of energy. Chemical reactions usually generate, those that are exothermic, they usually generate around kilojoules of energy. When we talk about nuclear reactions, we're talking about megajoules. Kilo is 10 to the third, mega is 10 to the sixth. So thousands of times more than a regular chemical reaction. And we are going to see that that energy is going to be associated to the mass that we are observing being changed. And Einstein gave us this formula that relates energy, mass, and the speed of light. So this is the power it comes. It's matter light or it's light matter. It's all combined. All at the end, everything one is the other. So let's see how we're going to apply this on nuclear reactions. So first, let's talk about what the mass defect is. So all this energy is going to come from the mass, like we're seeing here, and it's going to be due to something called the mass defect. And the mass defect is nothing more than this. For example, if I have hydrogen, which is one proton and one neutron, and I look for the specific mass of this isotope, it's going to tell me that it's going to be around 1.0007 atomic mass units. However, this nucleus is made out of one proton and 0 neutrons, so the total mass of this is the mass of a proton. And the mass of a proton is 1.00073 AMU. So if the hydrogen isotope is made only of one proton, remember we don't consider the electron because their mass is negligible, and the mass measured in the lab for one of these isotopes is 0.007, there's a variance in there. There's something that happens that when you take the mass of all the protons and all the neutrons, it never comes to be exactly the same as the mass that you actually measure on the lab. We call that the mass defect. And what the physicists have been able to figure out is that this difference in mass is because this mass have become energy, and it's the energy that keep the nucleus together. Remember we were talking about the strong force at the beginning, and we were saying that the neutrons kind of had to do with keeping the protons from flying away from each other. So this energy, this difference in mass is because some of the mass have become energy and is holding the nucleus, all the nucleons in the nucleus together. So that's what the mass defect is. So for example, to see how important this is, if I have 1 mole of uranium-238 and it decays to thorium-234, if I'm dealing with 1 mole, this is the difference between one and the other. So after I account for everything, this is my mass defect. I cannot account for where that mass went. If we consider that that mass is becoming energy, then we can use the Einstein formula to calculate how much energy that is. So which is nothing more than taking the mass, which is given in grams, so we're changing it to kilograms because 1 joule equals kilograms meter squares over second square. So since we know that we're looking for energy, we're gonna go for the joule, which use kilograms. So we're changing the mass to kilograms. We multiply by the speed of light to the square, and that gives us 4.1, negative 4.1 times 10 to the 11 kilograms meter squares over second square, or a joule. So like I told you before, chemical reactions generally are in the range of kilojoules of energy. Now we're talking about a nuclear reaction where the energy is on the order of 10 to the 11. Immense amount of energy coming from that nucleus. And like always, the negative sign means that that heat is being released. And that was only 1 mole. Imagine what 50 moles can do, for example, all of them releasing that energy at the same time. And if you keep imagining that, you may be observing a nuclear bomb or something on that order. There's another type of energy that we can calculate with the mass defect, and this is called the nuclear binding energy. So the one that we saw first is the energy that is released during a transmutation. But we can talk about, can you measure exactly the energy that is holding the nucleus together? So let's do an example with lithium. So if I have lithium 7, from lab measurements, we know that this isotope of lithium 7, which is lithium 7. So from measuring this on the lab, this is what we get. We get 7.016004 atomic mass units. We know that there's 3 protons and 4 neutrons, right? 3 plus 4 is 7. So I know the mass of a proton. The mass of a proton in kilograms is 1.6726 to 10 to the minus 27, but I can change that to atomic mass units by using the Avogadro's number to 1.0073. And the mass of the neutron is 1.0087. So if I have 3 protons, and this is the mass of 1 proton, that's the total contribution for 1 atom of lithium 7. I'm going to have 4 neutrons, and this is the mass of the neutron, and this is going to be the total contribution for the 4 neutrons. So the total mass of the nucleus is protons and neutrons, and that's what I'm going to get. If you notice, by taking into account the weight of every single piece of the nucleus, the mass that comes out is different from what we actually measure on the lab. So there's a mass defect in there. The mass defect is going to be 0.0407. So that mass defect on that particular nucleus of lithium 7, I can calculate how much energy is that. But for this, I like to measure this, or we like to measure this on volts units, specifically on mega electrovolts. And we have a 931.5 mega electrovolts for every atomic mass unit. So this is a conversion factor. So we're going to use that conversion factor there. We're going to multiply by the mass defect, and this is going to tell us that the energy holding the protons and the nucleus together in a lithium 7 nucleus is 37.9 mega electrovolts. So just to give you an idea, your dryer at your house uses 240 volts. We're talking about in terms of mega on this case. So immense amount of energy, just 1 atom So if you want to see how much that energy is for a whole mole, you're going to have to multiply that number by 6.02 10 to the 23rd. And that number is almost impossible for me to visualize what the amount of energy that would come out of there. So that's how you find the nuclear binding energy. How many protons, how many neutrons, compare that with the data you get from the lab. You can find your mass defect, multiply by the conversion factor from mass units to electronvolts, and that tells you how much energy is holding that together. So if it breaks apart, that's how much energy you will need to break it apart. So with that said, now we can apply this to the process of fission and fusion. Let's talk about fission first. So fission is what we use on our nuclear plants. It's also the process it's used on nuclear bombs and stuff like that. And it's nothing more than splitting a heavy nuclei. It can happen several ways. For example, if I bombard with, if I use neutrons to bombard uranium 235 atom, it can break two different ways. It can go this way, or it can go that way. And like I told you before, this is what we use on nuclear plants. So it's going to be generating energy, a lot of energy. And it's going to be based on the Einstein formula. So let's do the first one. And you're going to be doing the second one as part of your daily work. So let's do the first one. Calculate how much this energy is going to be based on this. Calculate the quantity of energy produced per mole. So we're going to be using per mole. So at some point, we're going to have to use that amount of atoms of U-235 with this mass, neutron-induced fission. So we're going to take uranium-235, and we're going to use a neutron to split it into tellurium-137 and tellurium, just give me a second. So tellurium is going to be atomic number what? If this was the class, you can tell me, but I'm all here all by myself, so I have to find it myself. Tellurium is going to be, just give me a second, number 52. To produce tellurium-137 and zirconium-97. And zirconium-97, and zirconium is going to be number 40. So we're gonna make sure that this is a balance equation first, right? So the atomic numbers, a total of 92 and 92. So nothing there. The atomic mass, 236, 6. See, 137 plus 97, that's 14, 13, 234. So that means I'm gonna need 2 neutrons to make it 236. So that's what I have in there. So I know the weight of what I'm dealing with, right? I know that the uranium-235 is going to be 235.043922 atomic mass units. I know that the neutron is how much? We said that the neutron was going to be 1.0087. (1.0087) atomic mass unit. So my whole right side, my left side, my whole left side is going to be 16, 9, 12, 5, 0, 6. So that's the total weight of my left side. My right side is going to be, it's telling me that tellurium is going to be 136.9253. Zirconium is going to be 96.90950. And a neutron is 1.0087, but there's two of them. So when I put all that together, I'm gonna get 0, 5, 14, 17, 26, 10, 23, 4 and 5, 18, 9, 15, 13. So I'm gonna get 235, 85, 36. So the difference between those two is going to be what? 236 minus 235.8537, let's say. That's going to be 9, 8, 9, 1, and 0. So my mass defect on this particular reaction is going to be 0.1989 atomic mass unit times the speed of light, 3.0 times 10 to the 8 to the square, and that's when I combine all the units, that will give me my energy in joules. So that's gonna give me an immense amount of energy, and then I'm gonna multiply by how many atoms I have on a mole, and that will give me my final energy. So that will be how we get to calculate the amount of energy produced by this split. So when you do your daily work, you get to do the second one. So what about nuclear reactors? And make sure you go to the textbook and check all those calculations in more detail so you can go step by step. So a nuclear reactor is nothing more than a fancy boiler. The energy that is produced by the electric generator just happens because you are creating steam, and the steam move the motor in here, it creates electricity. However, to create steam, you have to generate a lot of heat. So the heat happens because there's a nuclear reaction going on, and you're running a fluid across, and when it gets to the reaction, it gets really, really hot because of all that energy that is coming in, goes to the heat exchangers, boils the water, and the water produces the electricity. So the nuclear reactor is nothing more than a fancy boiler. However, it produces an immense amount of energy, but it had to be done very precisely. Very recently, during the tsunami in Japan, the Fukuyama reactor had a big accident with a meltdown, and the reason was that the coolant system failed. So when the coolant that is being run through the system to cool down the water that is going back into the reactor doesn't work, then it's gonna overheat and it's gonna melt the system, creating all the radiation. Before that, like 20 years ago, we had the big meltdown in Chernobyl in Ukraine. And what happens there was that the operators deliberately and in violation of the rules removed most of the controls and the safety rods. So they were trying to do an inspection and they didn't know exactly what they were doing. So they removed these control rods, which are designed to go in between where the uranium is generating energy. So these rods go in between and prevent the movement of neutrons into the uranium to keep bombarding the uranium. So basically the reaction got out of control, too much heat at the same time, and it melted down the reactor in a very simplified way. So like I said before, a nuclear reactor is nothing more than a fancy boiler, but you know I'm being facetious, right? A fancy boiler that requires a lot of expertise to control. And any variation or violation can cause the death of thousands of people and destructions of the environment. So what about nuclear fusion? And in addition to that, remember, uranium has a half-life of billions of years. After it gets a transmutation, it becomes thorium, which is also in the thousands of years. So you're generating a lot of radioactive material that is going to be around for a long, long, long time. And as of today, we don't know exactly what to do with it. Fusion is a whole different story. Fusion, you take two small nuclei and fuse them together. You're going to end up with a mass defect also, so that all that mass that is lost is because it's becoming energy. So fusion also generates a lot of energy, but not by splitting the atoms, sino by combining two atoms. That's exactly the process that happens on the stars. And the stars is what gives energy to everything we see. So two small atoms are being combined. If we can master this and produce energy, this would be the preferred source of energy because it doesn't generate radioactive weight. However, as of today, for this to happen, you need extremely high temperatures and pressures, which are the conditions you have at the sun and other stars. So you need so much energy to begin it that most of the time you need to initiate fusion by using a fission reaction sometimes. So based on this outlook, fusion will solve a lot of our problems, but it looks almost impossible to attain. However, I want to close this chapter by giving you hope. And I want you to watch this video, lasts about 2 minutes, and I want you to watch it with me before we close the chapter. So let's watch it together.
2, 1, 0.
This is the record-breaking reaction. It is more than 150 million degrees centigrade. 10 times hotter than the heart of the sun. And it happened here, the world's most powerful fusion plant, Jet Fusion, in Culham in Oxfordshire. It is, say the team here, a landmark for this technology.
These results are really significant because what we've managed to demonstrate inside Jet is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels, which is a major step forward in terms of our quest to get to fusion power plants.
Most nuclear reactors use fission. That's when big, unstable atoms like uranium are split in two, releasing lots of energy and radiation. Fusion is different. It involves forcing atoms of hydrogen together, fusing them to create helium, as well as lots of energy and just a tiny bit of short-lived radiation. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. Get it right, and it holds out the potential for producing almost unlimited supplies of energy pretty much forever. The key part of this reaction only lasts for 5 seconds and only generated enough power for 60 kettles, but it is an important proof of the principles of fusion. But it means there is still lots of work to do. Do you think you'll see commercial fusion in your lifetime?
Yes, I do think we will see commercial fusion.
You're confident we will?
Yes, I am confident. I want to believe in it.
So answer me this, why is it taking so long?
It is hard. It is really hard. It is very complex, but it's worth it, and we just have to do it for the future.
Fusion energy is carbon-free, but it is not going to be ready in time to get us out of the climate crisis. That shouldn't stop this research, say supporters. The enormous promise fusion holds means we've got to keep working on it. Justin Rolat, BBC News, Oxfordshire.
Tell me that wasn't exciting. This just happens at the beginning of this year. So the proof of concept that it can be done have been done. So
Think of nuclear power, and many imagine the world.
So we need people like you to continue this work and get us to a world where energy is available to everyone. So many things will be solved if we can do that. And with that thought, we are done with this chapter. We just finished fission and fusion. You have a kind of a quick tour of how a nuclear plant works. We talk about the mass defect. And overall, we talk about what nuclear decay is. We learn about how to do nuclear reactions. And we learn how to balance them. We learn about all the different particles that matter can decay by to become stable. We talk about the stability and how to identify, at least on a relative way, or exactly by using the stability belt graph, which ones are more stable than others. We saw how we can use radioactivity to determine how old something is. And like I said, we talk about fission and fusion and nuclear power plants. And with that, we come to the end of the chapter. So I know I'm going to see you in class again, but it's been a pleasure working with you. Hopefully these recordings were good enough for you to learn something from it. And I know you did a lot of work on your own. So I'm really proud of all the work that you did. And you hang in there to the end. So see you later. Let me know what I can do for you. I'll see you in class again, hopefully by the time you have finished watching all these recordings. So take care. Have a great evening.